Okay, today's lecture is about finite sets, countably infinite sets, and uncountable sets. It turns out that there are levels of infinity. And so let's take a look at this. We're going to start out with some basic definitions. And here, f is meant to be a function from a set A to a set B. We say that f is 1 to 1 if whenever a1 and ab are distinct elements of A, then f of a1 and f of a2 are distinct elements of B. Okay, so the distinctness of elements is preserved. Okay. Now, suppose we have a set S that's a subset of A. We can, given the function above, we can define f of S to be the sets of all elements f of little s, such that little s is an element of capital S. Okay. When we refer to, we will refer to f of capital S as the image of capital S under the map F. So if f of A is equal to B, if f takes the range exactly onto the domain, we say f is an onto function. Okay. This is the same as saying that for every B element of capital B, there is an A element of capital A such that f of A is equal to B. Okay, so now we're going to have some more basic definitions about functions. Given f from A to B as above, suppose that C is a set and that G is another function that takes B into C. Okay. Let's define another function, G. It's written G open circle F from A to C. Well, we read that open circle as composition, G composition F. So G composition F of A is just G of F of A. It is not difficult to argue that if F and G are 1 to 1, then so is G composition F, and that if F and G are onto, so is G composition F. Okay. We will now we will assume these things. You've probably seen their proofs in another class, so let's continue. When f is 1 to 1, there is a function f superscript -1. We'll read that f inverse, and it's just notational. Okay, that to the -1 is just notational to help us remember some things. But f inverse going from f of A, the image of f, back to A, such that f composition f inverse of B is B, and f inverse composition f of A. And to make it clearer, I should have put parentheses around those pair, is equal to little a. This function f inverse is referred to as f inverse, or the inverse of f. Okay. Okay, now just two more definitions. The definition of finite. We will say that a set F, a set S, is finite if for some n element of the natural numbers there is a function phi from the set 1, 2, 3 up to n onto S. Okay, so we're meant to, this phi is an onto function, so we apply, so each element of S has at least one element of the numbers from 1 to n that maps onto it. We say that a set is infinite if it is not finite. Okay. Yeah, this is, if I give this on an exam, this is, I'm being generous that day. Okay, so and here's a rule of mathematical writing, that your number of theorems should eventually be greater than your number of definitions. And so we have had definitions all lecture so far. At last, a theorem in the natural numbers is infinite. Okay. So what we're going to do is to show that whenever we have a function phi from 1, 2, 3 up to n into the natural numbers, then the image of that function will have a largest element, and from that we will show it follows that the natural numbers is finite. Okay, so it's an induction. So we'll start our induction with phi of 1. Phi of with n equals 1. Phi of 1 is the largest element of phi of the set of 1. Okay. Now suppose, and here I have a typo, that phi of 1 to k, I should have a closing parenthesis right there. Suppose that it has a largest element phi of L, and this L is one of these numbers from 1 to k. Okay, now again, I have another typo. I should have a closed paren here as well. So now let's consider the next set. Okay, it has one more element than the previous set, and that element is phi of k plus 1. If phi of k plus 1 is bigger than phi of L, then phi of k plus 1 is the largest element of that set. Otherwise, phi of L is. So from this, by induction, it follows that phi of 1 to n has a largest element. Now, how does this prove that the natural numbers are not finite? Well, let any n be given. Okay. Let phi of L be chosen so that phi of L is the largest element of that set, and we've shown it does have one. Note that phi of L parenthesis plus 1 is a natural number, but it is not in phi of 1 through n. Okay, so n is not equal to phi of 1 through n. Therefore, as n and phi were arbitrary, it follows that n must be infinite. And oops, I'm afraid we have another definition. Well, two more definitions. The definition of countably infinite and uncountable. Suppose that S is an infinite set, and that there is a one-to-one onto function from phi from the natural numbers to S. Then we will say that S is countably infinite. Otherwise, S is said to be uncountably infinite or simply uncountable. Okay, so some examples here. The natural numbers are countably infinite, and the open interval from 0 to 1 in the real numbers is uncountable. Okay, so classic result here. The set of prime numbers is countably infinite. They didn't use this language, but we can dress it up in today's nomenclature. Suppose that P1 through Pn is a complete list of all the primes. Okay, so that we have this so we have this function from the natural numbers, not from the natural numbers, from the numbers 1 through n onto the prime numbers. Now consider the number p equal to the product of all those primes plus one more. then p is greater than each of the pi's. Okay, yeah, for every I, so it's different, all right, and that p divided by each of the pi's has a remainder of 1 for every single I. Therefore, p is a prime number that is not in the list. Aha, so we have a contradiction.